the graph of this identity function, and if you have equal scale, x and y scale graph, it is a 45-degree line. So, no matter what value you put in, the same value return. Waiting to be opposed. Okay? Simple stuff. Now, something a little bit more complicated. If you have a function and then you multiply the function by a scalar. A scalar means a real constant, can be 0. And the limit of such a scalar multiple of a function, if this limit exists, then you can do something like you take out the scalar multiplier and work out the limit first. After doing this, you multiply the limit by the original scalar. You can rearrange the order of working. This one is the multiplication come first and then determine the limit. This one is the limit determine the first and then do the multiplication. Now this one is a number. So just a multiplication of numbers. Subject to the condition that this limit exists. If this limit does not exist, you cannot write something like this. You cannot. If you are talking about the limit of the sum or difference of two functions, it means the image of this one plus the image of this one for a particular same independent variable, or the image of this one minus the image of this one at the same independent variable value. Then the limit is equal to as if you determine the limit first and then do the addition and subtraction, provided that these two limits exist. If these two limits independently does not exist, then cannot. Now there is such a situation. The limit of this one exists, but you cannot do it like this because, say, these two functions are the same, in fact. So the difference between them is 0. It becomes a constant function. So the limit is 0. Or one is the negative of the other. So the sum of them is 0 again. Then the limit of this one is again 0. However, for these two, it may not exist. If this one does not have limit, this one does not have limit at this particular point, because we only talk about the point. So if this one does not exist, or this one does not exist, then we cannot write on this side, but this side well defined. Okay, it is a constant function. So it is not always true. It's only true when these two limits exist by itself. Multiplication the same, division the same. Okay. For division, of course, when you write in this way, the denominator, the limit cannot be 0. If the denominator is 0, you write it this way, it means that you are committing suicide. You just kill yourself. Now look at an example. Find the limit of this polynomial. Then if you break it down, it would be 3 terms. This one minus this one plus this one. And this is a constant function, so the limits must be the same. And this is a scalar multiple, so we can take 5 out. And this one is scalar multiple of a square function, so we can take out this scalar and then the square function. The square function means this one times itself. So it's limit of x times limit of x if this exists. So it is an identity function, so it returns the same as the input. That's why it is 2 times 2. Therefore, for polynomial, it is as simple as you just substitute. Just look at it as a function. Put this substitute in its true for all polynomials, because for any polynomial we can do such analysis. You break it down into terms, different terms connected by addition or subtraction, and then scalar multiple to take out the coefficients, and then for power factors, treat them as products. Then, therefore, for determining the limit of a polynomial, it is as if you are working out the functional value of. Okay. Very simple for polynomial. Therefore, we have different rules. Constant function, limit is always the constant. Identity function, limit is the value to be opposed to. And polynomial, just substitute into it. For this one, it is an example of the last rule. Whether we can do this depends on whether this one is existing and non-zero. Okay? Now, either of this one does not exist, we cannot apply this. Even though both exist, this one cannot be zero. Now, this does not have problem, it can be zero. Only this one cannot be zero. This one, we see, if we apply the rule, the denominator will be zero. So we do not apply the rule directly. Instead, we just factorize the numerator and then cancel out. Make the denominator does not have the problem. And when would it be having problem? It is when x equals 1. However, we are talking about limit x tends to 1, it means x is not 1. So we know that by having this one, we can substitute for make it simple. Over minus 1 is minus of this one. And it is minus x minus 1. And the limit is the limit of two terms. One is minus 1 times limit of an identity function, the other is a constant function. Okay? So the result is minus 2. Some other rules. For this one, for a polynomial, we saw it. The limit of a polynomial is the same as you substitute this into it. Similar to working out the value of a function. For exponentiation, you can do as though it is the polynomial, the same. Exponentiation works the same. Now, in the previous polynomial, for example, square 1 and x to the power 0, all the powers are whole numbers, integers. In fact, it is not necessary to be integer. It can be fractions, decimals. When it is fractions or decimals, it means that it is the nth root. It is to the power of 1 over n. And we can just determine the limits under the nth root before we take the nth root. Because if this exists and then we find its limit, then it becomes a number. We can consider the nth root of a concrete number instead of the expression. Now, before taking the limit, it can be an expression where the nth root will be too difficult. Say if it is log x, then what is the cube root of log x? It's too difficult to imagine this function. However, if we consider the limit before we take the cube root, then it is the limit of the log function. Log function is a continuous function. So long as now its domain is all positive real numbers. So whatever positive number put in here, the limit is log of this number. And then it is a number. It can be positive and be negative. If it is positive, no problem. If negative, it depends on the value of n. If it is odd number, no problem. If it is even number, say does not exist in real number set. Okay? So here is an example. This example is a polynomial, and if we do this first, no way that you can do. Then we determine the limit of the polynomial under the fifth root sign, and this is equal to easy to calculate. Just substitute 2 into the x, and then you find it is 8. So it is the fifth root of 8. That is the answer. Although it is negligible, but we know the existence of this limit. Here is another example, and this is a technique called fractionalization. Whenever you see something like this, no matter it is in the numerator or denominator or both, have such things, but think about whether we can multiply the conjugate of this one to it to see how it behaves. Now it talks about x tends to 0. So if you substitute x equal to 0 to the denominator, it will make you into big trouble. And so we try to multiply the conjugate of the numerator to both numerator and denominator, which we are going to do in the next slide. The conjugate of this one is copy all the things except changing the connector sign between them. If it is positive, change to negative. If it is negative, change to positive. So now it is negative. Multiply the same numbers, but change the negative to positive into both numerator and denominator. Now, since this is a positive non-negative number, this is a non-negative number, so add up to them must be non-negative. It can be 0, but never be negative. And you multiply the conjugate into both numerator and denominator. Before doing that, you have to check whether it is 0 or not. Now it is non-negative plus positive. So this part must be positive. So safe. Therefore, we can do this. And then simple calculation, you have this result. And with this result, you have x in the numerator, x in the denominator. We can cancel it out so long as x is non-zero. But we are talking about x tends to 0, so x is not 0. So we can cancel it out. Leaving behind is 1 over this. Up to this stage, it is safe to substitute 0 into the denominator and making it to be 1 over 2. That is one of the techniques of solving problems with the expression in such form, where you cannot directly substitute this value into the expressions. How about trigonometric functions? So long as the function's graph is continuous, no problem. You may just substitute into it, because there is a theorem for continuous functions. The limit is just by, the finding of the limit is just by substitution. And so it is easy to determine limit when we have the graph of the function. So for sine and cosine, just do the substitution as if they are polynomials. Substitute into it, determine the limit. And composite x opposed to a functional value. Now this is the image of a under p. P is a function. Image of a under p. And x opposed to this image. Image is a number. X opposed to this number under f. Okay? It means you work out this first as a function, and then use this as an output to be the input of this function, and then determine the limit. Now, what is the meaning of this composite function? Let me see what else. Now, a composite function is something like this. You have two machines. The criterion is the output of the first machine can be the input of the second machine. Then, if something like this, you get some input to the first machine and then it produces the output, and then this output get into the second machine, produce the final output. Now, it is not anything strange. We do it many times in your calculations. Say the function is, you work out the g function first, which is 2 times x, and then put it into the f function. So if you put 1 into this composite function, 1 times 2, 2 times 1 is 2. 2 put into f. Now, this is a g function. Okay? The g function is whatever you put in it, double it. So you put 1, the output is 2. And then you put this 2 into the f function. The f function is whatever you put in, add 1 to it. So 2 add 1 to 3. The output, final output is 3. If you put 2 into it, you double it to 4. And then this 4 put into the f function, it means add 1 to it, it becomes 5. If you put 3 into it, double to be 6. Put into the function f, it becomes 7. The fourth example, if you put 4 into it, double by g is 8, and then f add 1 to the output of g becomes 9. Okay? So the composite function is first by doubling and then add 1 to the result. 1, 2, 3, 4 produce 3, 5, 7, 9 in this simple composite function. It is the joining two functions. Mathematically, it is something like this. This is the whole function we call composite function. The symbol is like this: f and then a small circle g. The working is the right hand side one work first. So g work on the input first, and then the result feed into the input of f. The whole result is another function. It will fulfill all the characteristics of a function. Namely, for any input, there must be an output in the range, and the output must be unique. So it would fulfill both characteristics. Therefore, this one is a function by itself. And pictorially, it is the g function comes first, and it defines on the domain of g, and it produces an output which is its range, and the range is the domain of f, and the f has its range, and the range of f is the same as the range of the composite function. The domain of g is the same as the domain of the composite function. Sometimes we write in this way, sometimes we write in this way. This way is easier to interpret. Function of a function. Okay? Here is situation. When x is approaching to the image of another function at a particular point, seems like it is an input of this function, and we determine this limit. Then it is as if we determine the limit of this composite function. The input is to this function. The output is from this function, the same as this one. The input to this function, and then this one is the value to be approached by this one, and this x is the x for this function. Okay, this is the first input. The image of this one is the last output, the same as this one. This x is the first input, the image of f is the last output. And so these two limits are the same. Therefore, what we can do is we can do as if it is like this. You calculate this and then get x approach to this one for this value, for this function. Or you go to work out the composite function first. And if they are polynomial, then it's easy to work out this one and then substitute a into it. We have done this already. And so try this out. What is the limit when x approaches to 0? Now it is a piecewise function. The left hand side and the right hand side are behaving very differently in this function. So we have to determine the left hand limit and the right hand limit separately before we do any substitution. And so we do it. For the left hand limit, when x opposed to 0 from the left, it means x is a negative number. Because it opposed to 0 from the left, it is a negative number. When x is a negative number, its behavior is governed by this expression. When x is a positive number or 0, it is governed by this expression. So when x is getting close to 0 from the left, we have to consider this as the function. Therefore, this function, when x opposed to 0 from the left. Now this is a polynomial, so direct substitution works. This is cosine function, so direct substitution works. Therefore, we just do direct substitution into it. The calculation result is 3. When we approach 0 from the right, then it is governed not by this function. And so, this is from the right, and this one is 1 over cosine. So long as it is non-zero, we can do direct substitution. Now it is one by one consideration. When would cosine be 0? It is integer multiple of odd multiples of pi over 2. Odd multiples of pi over 2. So, but now we are talking about 0. It's very far away from pi over 2 or negative pi over 2. So it is safe. It is safe because we are talking about very close to 0. It is very, very far away that cosine of the x is 0. The first encountering is either on the left hand side, which is minus pi over 2, or on the right hand side, which is positive pi over 2. So if we are talking about 0, then it is safe. Then it is a continuous function, we can substitute into it. It is 1 over cosine 0, it is 1 over 1. And it is a constant, so the limit of x for this part is the constant. So 1 minus 4 is minus 3. And we see that these two are not agreed to each other. It means limit left hand limit. Now, both sides has limit, but they are not the same. They have limit, just like this example. This example. Both sides for the point x equal positive 1. Both left hand side and right hand side have limit. For the left hand side, x opposed to 1 from the left, the limit is 2. From the right hand side, the limit as x opposed to 1 from the right, the limit is minus 1. Both sides have limit, but their limits are not. So the limit as x opposed to 1 does not exist. Okay? Now, I would make use of the next 5 minutes to talk about something which I said that I would not do, I would not put into examination, which is the formal definition of limit. I would not put into any slide in case some students who did not come to the class and then only study slides for the examination, and always think that would be in the examination paper, and then complain to me that would be too difficult. And they would not say that they did not come to the class, they only say too difficult. That is usually the case. So I will not put it into the slide, instead I write it on here. I just do some simple explanation because in the past, most students find it too difficult. So I just do some brief explanation on it. Now, suppose there is a function. Of course, we are talking about limit of function. So f given f, a real valued function, as what we do in the tutorial questions. Real valued function. It means both is domain and codomain are the set of real numbers. F, a real valued function given, and is scalar C in the set of real numbers. It means that it is a real number. Okay? It is in the set of real number, it means it is a set real number. And other number, L, also a real number. Given all these three, a real valued function, a real number, another real number. Now, the definition of limit x tends to C for this function, this one, equals to f, equal to L. Now, suppose we say this, we are going to define this, okay? We are going to define this. Given real value function f, given this two value, now the C is this C, L is this L, okay? This L is this L, this C is this. I'm going to define this one. Now, how to define this one? Formal definition. The formal definition is, this one is for means. Means definition, okay? For any given, all math books use this symbol. This is a Greek, small Greek letter, epsilon, similar to E in English, which is a positive real number. Now, usually it will be written like this, epsilon greater than 0. But if you still have some problem, I would write it is also a positive real number. It means positive real number. Now, does not include 0, cannot be 0, must be positive. The same as this one, okay? It means the same. Given, for any given this positive real number, this symbol means there exists. Okay, there exists at least one. And other Greek small letter delta, the same as small letter D in English. But all math books use this symbol. This is called epsilon delta approach of definition. Just use these two to name such definition. This is also a positive real number, and it's the same as the books usually write in these two ways instead of these two. Okay, but they mean the same. Okay, such that the absolute value of the functional value, C, x, fx minus L, smaller than this epsilon, whenever this x minus this delta, smaller, C, not delta, x minus C, this C is this C, Okay? Means this one. This one. Smaller than delta. Now this is the formal definition. In my memory is for any given epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of fx minus L smaller than delta whenever x minus c absolute value is smaller than delta. I memorized this when I first learned this until today. When I explain to you, it is not so natural in my memory. That's why sometimes I write it wrongly. In my memory, I can always memorize this. I think I can memorize this until I die. Because when I learn this, that would appear in the examination. So I must memorize this. And my memory are these two instead of these two. But they are the same. They mean the same. Now what's the meaning of this? What's the meaning of this one? This one means what it means is, say, whether the limit of this function as x opposed to 2 is this one or not, is you tell me a value which is called epsilon. You put at here, positive or negative, positive epsilon, negative epsilon, you put at here, which form an interval, and then if the limit exists at here, I can determine another interval at here, which is positive delta and negative delta, which is on that side, epsilon is this epsilon, delta is this delta. Okay? So whatever the values of x within this small interval, they all fall in the 4 plus epsilon, 4 minus epsilon interval on this side. Now that is the meaning of this expression. And this meaning is so important. Remember in the video I showed you last week, the soldier and the turtle. And some of you are very clever. You told me that the problem of that thinking is due to I only think about the time before the limit occur, but not anything beyond it. Now you are very clever, you can tell this. However, how to overcome this? Because in that way of thinking, it seems nothing wrong. And so you will never be able to get into the time beyond the limit. Now that is the way. This way helps us to go beyond the limit. Because by using this way, we say whenever the x within this small interval, you get into the interval, you feel that the limit is there already. So by using this way, it keep the gap close, really agree to each other, and they are equal to each other. And so after doing this, we can go beyond. This one can go beyond the value of approaching. Now this is the way. It takes 2,000 years of human civilization to find this way, to overcome the problem that we saw last week. Okay? Now, if we have chance, we may consider this, discuss this again. Let us stop the lecture now, and before we dismiss, Happy New Year, and we will meet again after the Lunar New Year break. Okay, thank you very much.